All right, let's look at momentum problem types. So our first one is just plain old momentum. It's a momentum problem because I have a single mass in motion at a single moment in time. If that's true, I'm going to use the momentum equation, which says the momentum is equal to mass times velocity. And remember, direction is important, so the momentum's direction and the velocity's direction. Now, if I have a mass in motion between 2 points in time, I'm using the impulse momentum theorem. Okay, so the impulse momentum theorem is this. It has these 4 equations that are all equal to each other, J being the impulse, the average force over time, the change in momentum, mass, and final velocity minus initial velocity, that prime meaning final. Let's put some arrows on those to indicate they have direction as well, because direction is important. And so how this works is you pick any 2 of these, put them together, and that's how you generate an equation. So based on the information given, you pick 2, set them equal. Now, the next 4, the last 4 problem types here, all have a common thread. So what I'd like you to do is just put one of these little symbols off to the right or off to the left in the margin and say, okay, these are all conservation of momentum problems because there's no net external forces. Therefore, this is the equation I'm going to use. Add up the momentums of them before equals the sum of the momentums afterwards. Now, these 4 problem types all fall into that conservation momentum, but we just use this equation a little bit differently. So our recoil problem type, okay, we're back into the grid now. The recoil problem type starts together, ends apart. So because they start together, they have a common initial velocity. So we combine those initial momentums to have a common velocity. And we see that the change in kinetic energy is positive. We gain energy during a recoil. Typically, you can think about like someone throwing a ball. Okay, we converted chemical energy in those muscles into kinetic energy of the ball. Inelastic, this is when 2 things start apart, they collide, and they end apart. So start apart, end apart. In this situation, we have our conservation of momentum, assuming there's no net external forces again, but we lose kinetic energy. Energy is typically given off as heat, sound, or deformation. You can think about any car crash out there. There's sound created. Elastic collision. Now this is the rare one out there. Elastic collisions start apart and end apart just like inelastic, but kinetic energy is conserved. That means 2 things need to collide but never actually produce any sound, deformation, or heat. So this one is rare. Think about more of the molecular level or gravitational forces between 2 objects moving through space that never actually touch, but there's a gravitational force between them. In this case, we're going to use that same conservation momentum equation. There is no change in kinetic energy. What that means for me is that I have 2 equations. I have a conservation of momentum and a conservation of kinetic energy. So I can have 2 equations, 2 unknowns. And then the last type on this sheet, the perfectly inelastic collision. This is where they are very inelastic, meaning they don't bounce at all, they just stick. And so they start apart and together. So we have a common final velocity there. And energy is lost. So the change in kinetic energy should come out to be a negative number. So we lose some to heat, sound, or deformation. And here is our change in kinetic energy equation. You can write it in the elastic one, or you can write it down at the top or bottom. Again, look at the description down below for links to how to do each of these problem types in momentum.